זה המשוואה כאילו על המטען. כדאי לתאם את המשוואה על המתחים, ואז מה אני מתאר את השיעור בזה? כן. טוב, אז נכון, כאילו, זאת שזה אי נכון, כן, זה פתרון שזה כאילו, פתרון למשוואה הדיפרנציאלית אי דוט כן, זה אי כאילו, פתרון שזה אז פה יש לך עוד כל מיני קדמים ועוד זה כבר לא הומוגני אז יהיה לך עוד כל מיני כאילו הביטוי יהיה קצת פחות זה אבל בסופו של דבר זה אקספוננט כלשהו זה שאם תעשה את אפשר לעשות את זה שאם תעשה את המשוואה על המתחים תקבל שזה יהיה כנראה איזשהו v דוט שזה בדיוק ככה יצא v דוט זה משהו כמו חצי כמו
מי שבקורס דינמיקה אני רוצה להתחיל פשוט תגידי Yeah, well, send me an email more close to the due date, okay? And it's possible, yeah.
So I mean, I'm not sure yet if I'll even need it, but around Wednesday, if I need extra time, it's due on Wednesday.
Now it's due on Sunday. It's due on a Sunday, yeah.
Oh, okay, then that's
okay.
Fine.
Okay.
All right, so I'll send you an email in case.
Okay.
Thank you so much.
You're welcome. Ken. Okay. Is everyone here? I still need to wipe the boards, but while I do that, I have this table that I wanted to pass around last week, and I forgot about it, so please start filling this in. No, so mark somewhere that you're still not registered. Okay.
I will be affiliate now.
Okay. Okay.
So they mark or?
Well, then write it down. Okay. I opened the Moodle site, so you should be able to see the homework there, and also the file with all the administrative issues for the course, like what the grade is composed of. I also posted on the news forum that there is an extension on the deadline of the first exercise because I was late at opening the Moodle, so you didn't have access to the exercise. Is there anyone here that did not see the exercise because he is not able to access the Moodle? No? Okay. So today I'm going to complete the treatment we did last time for one-dimensional dynamics with showing you how we quantify the stability. Then I'm going to show you an applied model, a model of population growth. And then we're going to discuss numerical integration. This is very useful for this course and for doing computational research in general. And if we have time, we will start the topic of bifurcations that exist. They can exist already in one-dimensional dynamics, but then we'll see them also in two-dimensional and three-dimensional dynamics. And it's part of what makes these systems so complex. Okay, so last time we saw that we can classify a fixed point based on the graphical method only. So we have this plot of x dots as a function of x, and it crosses the x-axis at some point, and we say that this is a stable point based on our analysis of the vector field that is formed. And similarly, we say that this is an unstable point. And it's really simple to identify the stable point and the unstable point. If the curve is going down, is decreasing with x, it's a stable point. If the curve is increasing with x, it's an unstable point. So obviously, there is a way to formalize this and also get some knowledge about the rate at which the system will decay into the stable fixed point or the rate at which it will diverge. So what we do is basically we linearize around the fixed point. We say that compared to a system at a fixed point, we will take a system that is perturbed by a small amount. So if before we started, we had a system that we want to start at the fixed point, and then we know it goes nowhere, it stays there. Now we want to consider a system that starts very near to the fixed point. Okay? This perturbation we will call eta. So eta will be the state of the system minus the coordinate of the fixed point. This is just a small perturbation. Now we want to know what happens to this eta with time. Okay, we start the system from this perturbed state, and now where do we go? Then obviously what we are looking for is eta dot, the time derivative of eta. Okay, does eta grow with time? Does eta decrease with time? We want to know whether the perturbation will decay into the fixed point. So eta will be smaller and smaller. It will, the system will be closer and closer to the fixed point, or does it grow with time? So we just take this definition of eta, and we will differentiate by the time. So eta dot is equal to x dot minus d to dt of x star is just 0. So x dot, so we are left with x dot, which is just our original, according to our definition of a general system. This is f of x, and now we substitute for x again according to the definition of eta. Okay? So this is f of x star plus eta. So this is a certain point at which we know the properties of the system. We know that at this point f of x is 0, and this is a small perturbation. So what we do here, we do a Taylor expansion around x star. I'll write this here. Yeah? This thing, when you cancel things, and you just mark it, and you like to write that you cancel it to 0. Because this is constant. X star is constant, so it has no time derivative. So this part of the equation is just 0. This is how I marked it. It's a conventional way of marking it. So I do a Taylor expansion around x star, and okay, f of x star plus eta. First of all, I have the function at x star. Then I have the first order term, which is the derivative at x star times here I would normally write x minus x star, because x star is the point around which I am doing the Taylor expansion, but this is just eta. So, okay, I'll write this. Yes?
Can I repeat, please, what's the goal now? Why?
I want, yes. I want to know what happened. I want to get an expression for eta dot. Okay? So what I do is I linearize. I'm doing a linearization.
Near the x star.
Yes, near the x star. Yes.
Okay.
So this is my 0 order term, my first order term, I won't go into second order terms. This is just in the order of eta squared. Okay. So f of x star is just 0. F dot x at x star. I want you to know that when I mark f prime, when I use a prime to mark a derivative, this will be a derivative with respect to x, not with respect to t. So let's take a general variable. Y dot is in this course dy over dt, and y prime is dy over dx. So f prime x is the derivative of this curve. This curve is f of x. So I want its slope with respect to the x-axis. This is f prime x. And I want it at this point, at x star. So this this first order term, I can write f prime at x star times eta. This is just eta, according to our definition. And these are second order terms. Now, if this term is not negligible, then I don't care about these terms. Okay? This is linear in eta, and this is parabolic in eta. So since we are talking about very small etas, if this is non-zero, then this linear term will be larger than the parabolic term, the second order term. So what I'm interested in is this. Eta dot is approximately equal to eta times f prime of x star. So I see that eta dot scales linearly with eta. This is just a constant, right? So I have here a linear function of eta. And as you probably know, the solution to this kind of differential equation is very simple. It's just an exponent. And it can be decaying or it can be growing according to the sign of this number, of this constant number. So I will make here a table of the cases that we can have. F prime at x star is positive, or it can be negative, or it can be 0. So if it is positive, then eta grows exponentially. This is what I meant when I told you that we can learn something about the rate of growth or decay to the fixed point. So eta of t grows exponentially, and if you solve the differential equation, you will get something of this form. And this is positive. If f prime is negative, then eta decays exponentially. Again, eta. I'll mark here explicitly that this is negative. You have a negative exponent. And this relates to what I said in the previous lesson about how the dynamic system never actually gets into the fixed point. So, for example, in the exponential decay, you will never get to 0 if you are in the strict sense. So you always approach the fixed point, but never get there, at least in this type of solutions. When f prime is 0 at the fixed point, then this is a special case where we will have to consider the second order term. So now we can no longer say that the second order terms are negligible. They are the largest terms we have. And further analysis needed. And at this point, I'd like to take the opportunity and mention an important property of one-dimensional systems. One-dimensional systems always behave monotonously. So in a one-dimensional system, you can only approach the fixed point or go away from the fixed point, but you can never have an overshoot. So there is no situation where the driving force, the expression for x dot, is so large that if you are here, for example, it will take you beyond the fixed point, and then you will have to come back. We just don't have this in one-dimensional systems. Yeah, and so you have no overshoot, no damped oscillations, and no periodic solutions, no constant oscillations in one-dimensional systems. You can see this in these examples with the exponential decay, for example, of the perturbation. So as you approach the fixed point, the driving force, the f of x, becomes smaller and smaller and smaller. You will not overshoot. You can only approach the fixed point. Oscillations is something that we will encounter in the two-dimensional systems or in one-dimensional systems where time is discrete.
A mass with a string is not a one-dimensional system.
No, not in this approach, because in the equation of motion for a mass on a string, you have a second derivative. You know.
What do you mean by dimensions then?
So the dimension here is. Yeah.
The order.
The order. So here we have only a first derivative. Okay?
You meant something else.
Yes. So we consider a mass on a spring as a second order system. Maybe I'll show in a later lecture how to treat it, how to make it into a two-dimensional dynamical system. So there are no oscillations, no overshoot in one-dimensional systems. Okay, I'd like to show an example for this type of classification. This should be short. We have the system x dot equals cosine of x. And then when we want to find the fixed points, we see that x star equals pi over 2 plus k pi, where k is an integer number. So now, in order to know whether this set of fixed points, whether each fixed point is stable or unstable, I'd like to know the f prime at each fixed point. So f prime, you remember it's the derivative with respect to x. So f prime of x is minus sine x. Sorry. Without a minus? Yeah. I was right. And when we substitute the fixed points, we get minus sine of pi over 2 and this can be either minus 1 or 1. So when k is 0, just the minus sine of pi over 2, which is minus 1. And when k is 1, then we get the sine of 3 pi over 2. That's minus 1, but we have this minus. So k equals 1 goes here. So So 0, 2, 3, and so on. And here, sorry, 4, and so on. 1, 3, 5, and so on. So our fixed points are stable if k is even, and then we can go to the graphical method and check that this is right. So I plot x star versus x. This is pi over 2, this is 3 pi over 2, this is 5 pi over 2. So, and I can classify the fixed points according to the graphical method. So this is stable, this is unstable, this is stable.
Well,
Yeah, I made a mistake, right? Yeah.
I don't understand why if we got a minus for if we got minus for the f star, f prime is decays exponentially, but why does this say that this is
A stable fixed point?
Yeah.
Because eta is a perturbation,
Okay.
so this is what happens to it with time. Eta is just, it evolves.
It's like the distance from the fixed point when it decays.
What? Say it again?
The distance from the fixed point when it decays,
Yes.
getting close to the fixed
Yes,
point.
that's fine.
Okay.
So, okay, so I didn't make a mistake like I thought, because k adds to this, so this is k equals 0, this is k equals 1. So if k is even, we have stable fixed points. If k is odd, we have unstable fixed points. Okay?
This is with no regard to eta right now, because we didn't.
With no regard to eta?
Yeah.
We're done with eta. We used eta, we extracted this general rule, unstable, stable, needs further analysis.
Yeah, but
Calculate
here
in
we
the right
didn't.
time, right?
What?
But here we didn't use that distance. We didn't x minus x.
No, I no longer use it. I was only interested in this because eta allowed me to get a condition on f prime. The treatment with the perturbation and the linearization gave me a general rule, and I am using that. Okay. Question? Okay, so simple example, you'll have more on the exercise. Are you done with this? Now, let's look at a few cases where f dot equals 0. We'll see what we can do with that. So the first case I want you to consider is x dot equals x to the third. So the phase portrait will look like this. This is x to the third, and I have a fixed point here, and the field looks like this. So obviously this is an unstable fixed point. So from here it's clear that x star equals 0 as well. F prime of x is 3x squared, and when you substitute 0 inside, you get 0. So this is one of the cases where we said we might need further analysis, but we can actually know something from the graphical method. The second case, x dot equals minus x to the third. X dot. So this is the plot, and the field looks like this. And this is a stable 6-point. And it's very similar. So x star equals 0, f prime of x is minus 3x squared, f prime at x star is 0. So here we can't get a classification from the linearization, but we can get something from the graphical method. Next case. X dot equals x squared. So again, you immediately know that x star equals 0, f prime of x equals 2x, and f prime at the point x star equals 0. And when you plot x dot versus x, you get this. You can plot the vector field, so it looks like this. And you see that this is a case that we didn't have before. If I am at a negative x, then I'm drawn to the fixed point. I'm gradually drawn to it in a force that's decreasing and decreasing. But if I am at a positive x, I'm drawn away from the fixed point. So this is what we call a half-stable fixed point. There is a side where it is effectively stable, drawing any phase points that are on this side, and there is another side on which it will reject all the phase points. So I mark it like this. It's a half-filled circle, where the half that is filled is on the stable side. So this is a half-stable fixed point. This kind of behavior becomes very interesting when we go to 2 dimensions. So when we go to 2 dimensions, we'll see a 2-dimensional space where there is this type of dynamics, and we call it a bottleneck behavior.
Why is bottleneck?
You'll see later. You'll see in the 2 dimensions why it's bottleneck. The next case is the trivial case x dot equals 0. So here x star is just any x, right? F prime of x is also 0, and you put any fixed points there, and you get 0. So you don't know whether it's stable or not. So here, this is the plot that we must make, and this is a whole line of fixed points. So if you are on any point on this line and you are perturbed, you will just stay there, and there is no driving force. You can be stable and stay anywhere on your x-axis. We'll see how to classify the stability of this. I mean, the terms for stability of this kind of fixed points will be given later. We will go into more formal definitions of stability. Okay, I'm going to wipe this away. Next thing I want to show you is an applied model of a one-dimensional system, and I hope it will convince you that these systems can be interesting, can tell you something about the real world, about the natural world, at least under assumptions that we make. So this is a model of population growth. So we want to know about a certain population, given a starting point, given the number of individuals that we have at a certain point in time. We want to know whether it will grow, whether it will decay, at what rate. So we can build models about it. And the simplest thing would be to say that the number of individuals changes in time in a way that is proportional to the current number of individuals that we have. So these are all the individuals that can reproduce, and according to some reproduction rate, you have the change in your number of people or bacteria or whatever. So this is
Why linear?
what?
Why linear?
Say again?
Why it's linear? Just this model?
Just I think just for simplicity. But, yeah, a very old model, and you may have heard the term Malpighian Growth. So the original way of thinking of the way populations grow was this, and the solution is just n of t equals n0 times an exponent of RT. That's an exponentially growing population. But we all know this is not realistic, right? Although human population gives us reason to think that it might be realistic, but we all know that this can't be supported by nature. So there are obviously limited space, limited resources, and we'd like to put that into the model. So we'd like to have a condition that has what we call the per capita growth rate we'd like to have some condition that has this term decrease when we approach the limit of the resources. Or even this term should become negative when we are past the limit. We want the population to start decreasing if the limit was surpassed. So the way this is commonly done is this n dot equals Rn times 1 minus n over k, where k is called the carrying capacity, meaning the carrying capacity of the environment. So you can see if the population becomes larger than the carrying capacity, this term becomes negative and the population should start decaying. And as long as this is small, then the population continues to grow. Okay, this is the model that we are going to look at. It's called the logistic equation. And it's also very old. It was devised by Euler in 1838. And it's a very simple model, and it still serves, I think, as the basis for population models. I'll say more about that in the end. In the homework, you have a version of this model. So when we are given this kind of equation, we immediately want to say, are there fixed points? Are there values of n where the population is stable? And what happens in between? So the first thing we do is we try to set n dot to 0. So obviously we have the first n star at 0 and the second n star at k. And we'd like to have the phase portrait for this system. Now, since we are dealing with populations, obviously n cannot be negative. Also k, the carrying capacity, there is no sense. What?
Bigger than bigger or equal.
Yeah, there can be a zero population.
Just said.
What?
You just said.
It can be
It will
negative.
just not grow. It will stay at 0. If it's 0, it will just never
Not
grow.
interesting, yeah.
You
No, but negative is not physical. Zero is physical but not interesting.
trying to compare between two populations, the relationship.
No, there is only one population.
So what's n1 and n2? 2 point times?
These are two fixed points, n star 1 and n star 2. Right, so I'll mark n equals k here. So we know we have two fixed points, one at 0 and one at k. And the shape of the curve is very similar to the curve that we saw in the last lesson, x times 1 minus x. Right, so near 0, it's approximately linear, and then it starts decreasing like an upside down parabola. So already we know the stabilities here, and we can plot the field. Okay, this is the field. The slope here is approximately equal to r. Okay, because n is very small, so n over k is very small, and this term is approximately 1. So n dot is approximately Rn. So when the population is very small, it's you can say it doesn't really feel the limitations of the carrying capacity, and it grows similarly to a Malpighian population. However, as it grows, it starts, around here, it will start decreasing the rate of growth because it will start feeling the constraints of the carrying capacity, and gradually the rate of growth will be smaller and smaller. Now, we can plot the solutions to the differential equations based on our graphical method.
It can go too negatively, right? I mean, if it can be more negative than the amount of people or whatever in the population.
Say again?
It can go to the negative, like it can be
Here?
too negative, yeah.
This is just the rate. So if it is here, then the rate will be negative and it will decrease.
Right, but the rate can't be higher than the amount of people in the population. It's not possible that more will die than the amount of people, let's say, that I have in the population. Right? if I have 10 people in the population, it's
Yeah.
not possible that 11 people will die.
No.
You can go from a person per day to a person per minute. You can also die faster.
So it takes less time to die.
Yeah, you can die faster. You can't. This is a model with continuous time and continuous population. So if you have it, yeah, it's not that you can't have 11 people die if you are 10 people. So let's see in the solution. Okay. I forgot to use the black pen today. On the internet it shows more clearly. So this will be K. Actually, I can mark a solution here. Okay, if you are at the carrying capacity, you will stay there, as we talked about. If you are at 0, you will obviously stay at 0. Oh, this is your... What?
The y-axis is it n?
Here, sorry, the y-axis is n. Yeah. If you start above the carrying capacity, so the rate of growth is decaying. If you are very close, it's a slow rate. If you are more above the carrying capacity, it's a higher rate to begin with. And here, this is similar to what we discussed in the previous lesson. If you're close to the carrying capacity from below, then you grow at a small rate and approach the carrying capacity. Here you grow at a maximal rate, and here you start with a slow rate, and then you go to a higher rate. So you have sigmoidal curves here. So these are called the solutions of the differential equation. Like I mentioned in the last lecture, each solution requires an initial condition. So these are the initial conditions, and each initial condition determines a unique solution.
The sigmoid is at the peak of the between the k and 0. The sigmoid.
Yeah. So at this peak, if you start at the population that corresponds to this peak, you will have no sigmoid. You will already start at the maximum growth rate. If you start below this, you will not start at the maximum growth rate, but you will reach it pretty quickly. And here, you will take time. First you are very slow and then very fast. This is what makes the sigmoid shape. Okay, so what I wanted to say about your question from before, Neil, I think.
Yeah. We'll go back.
Do you realize?
Yeah.
So at each point, you can't lose more than you have. This is this type of decay. Similar to half-life decay. Okay, before we take a break, I would just like to say that this type of model proved quite successful in describing populations of yeast, for example, under very certain conditions, like no predators. Okay. Also, I wrote this down here. Constant climate and constant food supply, but a limited space, for example. So, and the sigmoidal growth of the population is very typical for this type of simple creatures. When you go to other more complex organisms, you start having more complicated life cycles, for example, and you also sometimes need need to add the probability of finding a mate if you have two sexes in this organism. And so populations of more complicated organisms can show fluctuations, for example, due to the life cycle, for example. So the model is simplistic and works well for simple organisms. And the field of population models is there's a lot of work on it, and you can find even papers from recent years considering different aspects of population growth, of limitations, of the environment. Sometimes they include space, so there are also spatial models. Okay, so you'll have a version of this in the exercise, and I think it's interesting, and we'll also see population models in 2 dimensions when we get to 2-dimensional systems. And then you have predators and prey and competition, and it becomes very interesting. Let's take a break, 10 minutes. זהו, אבל אני חושב שזה נראה לי באמצע השיעור. תגיד גם מתי תיגמר. תיגמר בהתחלה.
יכול לבדוק כמה שבעצם מספיק עם כל הקבוצה?
כן. אתה מתחיל מאיזושהי נקודה על הציר הזה, וזה מההתחלה. ואז אתה יכול לבדוק פה עבור אותה נקודה מהגודל האחר שאמור לדחוף אותך. ואז בעצם אתה מדמיין איזושהי נקודה שהולכת פה לפי אפקטיביות. פה היא מתקדמת בקצב בינוני, קצב יותר מהיר, ואז היא הולכת ומאט. זה. הקצב שלה מאיץ ואז מאט.
אמרנו שכיוון החצים הוא לפי הסימן של ה...
כן.
יש לי מה לעשות. לא בקטע של לספור קורסות.
אמרנו שזה סטייבל.
אני לא יודע אם נלמד שם משהו.
כל ש-X גדל, אז
הוא עושה מלא פרויקטים.
דריבטיב קטן, נכון?
לא יודע כמה כוח יש לי.
כן.
נכון, זה לפי הגדלה. שזה ראינו את הדוגמאות. אבל נכון, זה פה. אבל מה קורה פה עד לנקודת המקסימום? כל ש-N גדל עד לנקודת המקסימום, ה-N דוט גדל.
נכון, טוב, אנחנו מדברים על הסביבה שלה. היא לוקלית סטייבל.
בדיוק, לוקלית סטייבל. אז זה לא כל כך נכון לצייר פה, אלא אתה יכול לצייר רק מהנקודה הזאת לפה. זה נכון רק עבור האזור הזה, לוקל, נכון?
לא, אגן המשיכה שלה, יש לה אגן משיכה. אנחנו נדבר על אגני משיכה בהמשך. אגן המשיכה שלה הוא בעצם מגיע עד פה. מפה ועד לפה. פה זה כבר, אם היה לנו אין שלי, אז היה פה אגן משיכה אחר שמשיך עד פה.
וכל התחום של סטייבל סטייט, מה שדיברנו בשיעור החצי שעה, למה זה בדיוק שייך? אתה יכול לתת פה איזושהי אינטואיציה?
כן, בטח. סטייבל סטייט, לדוגמה מתח ממברנה של נוירון. זה סטייבל סטייט. זה מפריע לו קצת לצורך.
אולי מודלים של נוירונים שרשתות שמשהו מתכנס למשהו, אולי...
נכון, הטרקטורים ברשתות הם סטייבל סטייט.
אני לא בטוח שזה one dimension, למרות שזה לא חייב.
לא, זה לא one dimension. זה ממש, אם אתה רוצה על one dimension, אז זו דוגמה מצוינת. אוכלוסייה שמתאזנת על איזשהו דעיכה רדיואקטיבית, נגיד. כן, דעיכה רדיואקטיבית היא פשוט הולכת לאפס לסטייבל סטייט שלה. מה עוד? יש לך לפעמים אולי ריאקציה אנזימטית או ריאקציה כימית משקל של זה ככה.
טוב, תודה. היי, רציתי לשאול, הטבע אקספנשן?
כן.
אז חשבתי לזה לפי x, חשבתי שכאילו x זה הקבוע ואתה זה המשתנה.
טוב, x זה המשתנה המקורי שלנו. אז עשינו פיתוח למשתנה x סביב x תג, סביב x כוכב. בדרך כלל זה קצת מבלבל ולא כתבתי את זה בצורה המקובלת באמת. בדרך כלל אתה עושה פיתוח סביב x מינוס x 0. אז מה שאנחנו עשינו
0 פחות x.
זהו, אז אנחנו פשוט אמרנו ש-x פחות x0 זה x כוכבית. כן, עשינו פיתוח ל-f של eta באמת.
לא, למה באמת אתה רשום לך אפילו x, לא רשום את בשום מקום, כי רשום x פחות x. כמו שפה התכוונת לאתה?
אז פה התכוונתי באמת לזה, ואחרי זה הפכתי את זה באתה. ככה יצא לי אחרי זה eta כפול f תג.
זהו, כאילו צריך, כל משוואה מתכנסת כל משוואה מתכנסת לזה.
הנה, פה האתה הזה זה בעצם הדבר הזה. זה f תג x ב-x תג, זה תג הזה, זה
אז בעצם כל המשוואה מתכנסת f תג x כוכב כפול eta.
כן.
כאילו זה המשוואה שווה בעצם לכל זה. זה פשוט כאילו בעצם, אוקיי. בסדר, תודה. ורציתי לשאול לגבי גודל השיפוע, אני פשוט לא טובה להעריך את זה בצורה ויזואלית, אז המקסימום שיפוע פה, זה כאילו, זה תמיד בנקודות, כאילו זה משתנה, זה שיפוע גדול יותר מהשיפוע פה?
רגע.
אני סתם לא טובה מזה אינטואיטיבית.
יש פה שני דברים. יש את השיפוע פה, אם אני אומר מה השיפוע פה, אני מתכוון לגודל, לערך של העקומה על ציר y, על ציר m דוט. אז נגיד בנקודה הזאת, אני מדבר על זה. ובנקודה הזאת הוא מקסימלי. זה הגודל של m דוט, כי פה השיפוע הזה הוא m דוט.
כן. אבל פה, בפונקציה הזאת.
כשאני מדבר על השיפוע שלה, אז פה זה שיפוע 0.
זאת אומרת, שהשיפוע הכי גדול הוא דווקא באזור הזה, ולא פה. פה הוא קטן.
נכון, השיפוע הכי גדול.
אין כי אני רואה משהו פונקציה שהולכות כאילו ככה, כאילו פונקציה שהולכות את הרגולות, אז שיפוע קצת קטן פה. נקודות שינוי. כאילו לעומת פה, נגיד שפה שיפוע גדל.
לא, אז מה שהשיפוע של העקומה הזאת מייצג הוא קצב שינוי השינוי.
כן.
כלומר,
זה אינטואיטיבית, אני פשוט לא טובה כל כך להסתכל ויזואלית ולהגיד איפה שיפוע גדול. כי פה ממש רואים שזה מתקשר, אבל נגיד פה לעומת פה, אני לא יודעת.
כן, לא, אני לא אמורה לדעת פה לעומת פה. אני רק אמרתי שהשיפוע פה הוא R.
אוקיי. אז זה גם חשוב שם בבית, אז נגיד השיפוע פה ושיפוע פה הם בערך אותו דבר?
כן, אם תסתכלי מספיק קרוב הם חייבים להיות אותו דבר, זה כאילו מי יכולה לעשות פה לינאריזציה.
עכשיו, זהו, אז שיעורי...
מספיק קרוב, אז יכול להיות שפה זה יהיה יותר קטן ואז זה יחסר יותר גדול, אבל לא יודעת.
אוקיי, עכשיו בשיעורי בית, אז היה משהו שלמדנו עכשיו על הדרך הזמנית לקבוע נקודות שיפוע, זה מה שלמדנו עכשיו. ולא התכוונת בשיעור הבא שכאילו כמובן שנפתור את המשוואות, כי אני פשוט צריכה לפתור את זה ולא לצייר, ואז נראה שזה
יש מקומות שאת אמורה לפתור, בשאלה הראשונה את אמורה לפתור משוואות,
כן,
בשאלה השנייה לא.
אוקיי, טוב, כי פתרתי היה שם משהו התחלתי לפתור את זה ולא לצייר, אבל בסוף קראתי שזה לא רציתי לשאול אותך על זה, כי יש שם דברים קצת מסובכים, וגם בסעיף האחרון של האלן, עליה היא...
אליפט, כן.
כן, גם שם לא צריך לפתור? צריך פשוט לוותר לפי ה...
לא, אני לא צריך לפתור. כמו שאתם פה.
אז זה מה שרציתי שלך חזרה נראה לי.
אפשר שתי שאלות,
כן.
משהו של טרמינולוגיה. אפשר לקרוא למה שאתה קונה half stable, unstable? ככה אני מכיר את זה.
כן.
כן? סבבה.
פה בקורס נקרא half stable.
אבל כשאני כותב לך, אני כתבתי unstable. זה לא יציב.
פה בכוכבית.
לשנות את זה?
כן.
כשאני קצת חזר, אני לא חושב שזה משנה לי איפה זה. יכול גם סיגמואידים ו...
כן.
כאילו
אם יש שינוי שוני איכותי בין פני ההתחלה, אז צריך להראות אותו.
צריך להראות ממש. צריך להנגד את זה קטן.
כן,
אז להראות
זה
את זה?
שוני איכותי.
אפשר גם לשאול כאילו, לא בקטע שיש לי איזה ביקורת, אולי פשוט ככה הקורס.
כן.
אבל זה כאילו יותר מעניין כל הדברים האלה, לא למדתי שום דבר חדש.
כן, אני לא יודע מה בדיוק למדת, זה יהיה יותר מעניין בטוח.
אנחנו כל הזמן בסדר, מסתכלים יש נראים פתרונות במחרפזה
כן. שזה נהיה בשני ממדים, זה נהיה יותר מעניין.
אז מה, אז נראה אוסילטורים אוקיי.
תראה, אתה פיזיקאי, יכול להיות שהקורס קצת קל בשבילך, כן? לא עושים פה דברים מסובכים. אני לא יודע למה אתה מתכוון מעניין. אני חושב שזה מאוד מעניין שיש אוסילציות בדו-ממד.
כן, אבל עשינו את זה כל כך הרבה
אתה עשית את זה.
מכניקה אנליטית, מכניקה סטטיסטית, גלים, זה מופיע בכל דבר כאילו. כאילו כמה זמן אנחנו לפני פשוט שאמרתי סטוכסטים, דבר של סטוכסטים וקיוס, זה אני לא מכיר בכלל.
כן.
מתי נגיד?
אבל בזה נוגעים, כאילו זה בשליש האחרון של הקורס.
עכשיו, 5 שבועות זה יהיה כאילו...
כן, זה דו-ממד. נגיד, למדת לסווג נקודות שבט בדו-ממד?
איך?
לסווג את נקודות השבט בדו-ממד? אם יש לך מערכת דו-ממדית, מצאת את נקודות השבט?
אתה מדבר משוואה דיפרנציאלית בסדר שני, זה מה שאני מפרש את זה.
אוקיי, נניח שאתה לא יודע לפתור אותה.
כן, אני ראיתי, יש גם פתרונות מרוכבים, עושים ספירלות החוצה, בצורה הזאת, בצורה השנייה.
אז זה מה שנלמד.
ראינו את זה כבר.
מה זה ראינו? אתה ועוד אנשים?
לא יודע, נראה לי כל מי
א', לא רגילים להרבה פיזיקאים. זה לא שיש הרבה פיזיקאים שבעיניי
לא,
סטטיסטי.
כל הפיזיקאים לא כמוני היחיד. כי הם כבר, יש לי כאילו 3 פיזיקאים במחזור, אבל הם כבר עשו רשתות באפס.
אוקיי. כן.
הם לא פה.
כן.
טוב, אני אשאר בינתיים, אני אראה כאילו...
אוקיי. מה עוד יש? ביפורקציות. אני לא יודע אם נכנסתם לזה. לא? אז ביפורקציות זה יותר מעניין. לא? זה כשאתה משנה את מספר נקודות שבט, היציבות שלהן, דברים כאלה, ואתה יכול לעבור מהתנהגות אחת מהתנהגות אחרת. זה מאוד שימושי כשאתה מתעסק ברשתות נוירונים, גם בקורס וגם באופן כללי. כי ברשתות נוירונים יוצא מאוד יפה שיש במודלים של רשתות נוירונים. יש נקודות שבט ופרמטרים מסוימים מעבירים אותך ביפורקציות ומבצעים לך נקודות שבט וכאלה. זהו, אז אם ראית את כל העניין של נקודות שבט בדו-ממד, אז באמת לא... ברוב הקורס... יכול להיות שיהיה לך כמה נקודות שבט.
המודלים האלו הם ניסיוניים או שזה פשוט הנחות המודלים שעכשיו הצגתי?
כן, לא, אז זהו,
או שזה הנחות שאנשים...
אז זהו, שהמודל שהצגתי עכשיו הוא מודל, הוא לא ניסיוני, כן, מישהו ב-1838
תיאורטי.
כן, תיאורטי, אבל כשמפעילים אותו על אוכלוסיות שמרים אז אפשר להתאים אותו ככה למשהו ניסיוני.
הוויכוח היה סתם תיאורטי, הוא אמר טוב יש לי אין אנשים, השילוב
כן,
בקצב יהיה שיפוע מסוים כפול אין אנשים הזה, זה פשוט...
כן,
אוקיי.
השיקול היה תיאורטי.
הבנתי. וגם התיקון היה תיאורטי.
אני חושב שגם התיקון היה תיאורטי.
אוקיי, זהו. מעניין.
בואו נחזור, שיעור. יש לך שיעור בשיעור הקודם?
כן.
איזה?
לא בביולוגיה.
אוקיי. טוב. אתה יכול לאכול. I'm moving on to the subject of numerical integration. This is a very useful tool, both to verify what we do in the analytical or geometric treatment, and both to try and say things about very complicated systems, or actually not so complicated systems. Sometimes we'll only be able to treat the very simple systems with our tools, and then if we have something just a bit more complicated, we'll have to do simulations and see what the simulations give us. And see if by simulations we can find fixed points or oscillations or bifurcations, which we'll get to that in this lesson. So it's very important to know how to do integration over our systems and get numerical solutions. It's a very, very powerful tool. You'll also do this during the course. You'll have exercises with running computer simulations of models that are a bit more complicated, models of neurons, for example, maybe populations. We'll see. Okay, so we'll start with the most simple way of integration. We are given a dynamical system, and we're given an initial condition. So following some short time that we will mark as delta t, we expect that x at this point in time will be x0 plus dx dt at x0 times delta t. So this is the most simple way that it will go. And I can mark this, for example, as x1. Just take your initial value of x, you find the derivative, the time derivative at this x, and you multiply the time derivative by the time that's passed in order to get your new value of x. So I like to draw this graphically. Say you start at time t at some x0. Now you have your f of x. So you have your f of x, which is a function giving you the time derivative for any value of x. Let's say so let's say according to that, this is your time derivative, this slope, and you would like to know at t1, which is t0 plus delta t, you would like to know where you should end up. So this is just making the assumption that the derivative is approximately the same for all the values of x that you are going to pass during this short time interval.
And you also assume that it's linear, right?
Yeah. This is an assumption, and you kind of say, well, if my delta t is very, very small, then this assumption should be okay. Right?
Just taking the first Taylor expression.
Yeah. Yeah. So what we are doing here is basically we are multiplying the slope by the interval, and we are trying to get this change in x, this delta x. And so we can write the general rule: x of n plus 1 equals x of n plus f of xn times delta t. This is called Euler's method. And it's a first order method, like Hagai said. It takes the first order term, the linear term, and multiplies it by dt. You will be, in the next exercise, you will be required to implement this in a program. This in the next method. Yeah? Any question? Okay.
So you just did it,
Where did you do it?
in your network, you implemented this,
Okay, so you have the code ready.
the code already.
Yeah.
I just have to put different f for whatever you're going to give.
Yeah. Did you look at the errors that you get with this?
Like comparing to what delta I'm taking. No.
Okay. So obviously, if the time derivative at the next point is not as you assumed, you will get to a different x, right? So this is not this is not the real situation that I want to illustrate. This is t, this is x, and you start at x0. And the real function that you want to integrate, I'll mark it with blue. Oh no. The real function, say it goes like this. And your next point is here. This is your delta t. So you are trying to find this value of x. This is your x1. But you assumed such a slope. So you overestimated x, right? And you can imagine that when you go from one delta t to the next, you will accumulate an error. So this method is very inaccurate. And it requires that your delta t will be very small.
Or taking a bigger series.
Exactly. So, like Hagai said, the way to make this more accurate is it can be to take higher order terms, right? To start taking second order terms and third order terms. You can do that. What we are going to see here is still a linear method to try and improve the performance of this type of method. I'll just say that you can use the Euler method in simulations as long as your delta t is small enough. And by small enough, I mean at least small by an order of magnitude from your minimal time constant in the physical system that you are running. So say you are running a simulation of a neuron, and you have time constants, for example, the membrane time constant. The membrane time constant is 1 or 3 milliseconds. Then you would like to run it with a delta t of at least 1/10 of a millisecond. I mean, either 1/10 of a millisecond or smaller, in order to avoid accumulating such errors. And you can also use the higher order methods that I'm going to show now. So the next method is called the improved Euler method. And it's a second order method. Not because it takes square terms, but because it takes 2 steps per delta t. So first we do some kind of probe or trial step. Call this a trial step. And I mark it with a wave here. And the trial step is just the first Euler method, just the evaluation of xn plus 1 that is made by the first Euler method. So I already showed you what that is. This will give you this in my illustration. This is xn plus 1. Now, now we construct, we take an average of the slope at xn, the slope of at xn plus 1. The xn plus 1 that we got from our trial step. So this is this slope. No, sorry. To get this slope, I have to extend my blue line. This is this slope here. Okay. So here, in order to get an estimation, some slope on which I will do the integration, I'm not taking this as in the first order method. I'm making an average of this and this, hoping that it will be some representative of the slope in the interval delta t.
What is this?
Where?
In the graph?
N plus 1 wave.
This one.
Oh.
This is this value here. So this was our estimation according to the first order method, and this is the slope that matches this value. I'll mark this as f wave. And no, I'm just marking it f wave. Xn plus f wave times delta t. And this is what I use instead of f of x of n in order to get my final estimation of xn plus 1. And I call this a second order method because I have two steps, this one and this one, for every delta t that I want to integrate on.
So you have first to estimate x1, right?
Yeah, I use this in order to estimate the x wave. And then I took, yeah, and then I took the x dot, the slope that's predicted for this value, and averaged it with the slope at my present value. And then it's an estimation. It's kind of acknowledging that the slope at my present value does not represent the slope along the whole interval dt. I'm saying the slope of the real function at the interval dt is not the slope of where I am now. It should be something else. So this is some estimate of that slope.
But here you take xn and xn plus 1 and you do the intermediate.
Yeah. I take the slope.
So you want to get a point between x1 and x0 because I just don't get the objective of this.
No, I'm acknowledging the possibility that if I do only this, I am either overestimating or underestimating the next value of x.
Okay, this one is clear.
And this is based on the slope at x0, at where I am now.
Okay.
So I'm saying this slope is not a very good predictor. So I need to correct it somehow. So in order to correct it, I will take, this is a kind of probe. I will take I will make an estimate of what xn plus 1 is. This is my estimate. And I have a prediction for the slope there. And so the slope that counts for the interval dt should be something intermediate between these two. And I'll just take the average, because I don't know which one should be more dominant. I just take the average. What?
You can do it again.
Yeah, I can do it again and again. This is somewhat. Where?
Over there it should be as per the weight and stuff.
This? No, doesn't have to be. This is the same function, but this is what you put into the function. This? This?
Yeah, this is not the same x as the second line.
It is.
Okay, so it should be marked with a weight.
Is the first prediction?
This is the regular f from the definition of the system. This and this and this is the same function. It could be the function x squared or e to the x or something like that. It's just a function.
What you're doing is not taking the f weight you wrote on the middle row and put it on the first row.
On the middle row and put it in the first row?
Yeah. This is what you do, right?
No. I take the f from the definition of the system, and I do this exactly as in the first order method, and I get some tentative xn plus 1. But this is not my final decision, right? So I mark it with a wave. But I use this to get the x dot that matches it. So I got the f of my present x, and the f of my estimation of the next x, of my initial estimation, and I average them, and I use it here.
And is there a theorem about if you take n to infinity, given times to do it?
What do you mean?
If I do this process like over and over again,
Yeah.
I don't average 2. I will take the new estimator, will put
Yes.
it, plug it
Okay.
in, I will divide by 3,
Yes.
do it over and over again.
Yes. I don't know. But what matters here is that as you add more steps, you increase the cost of computation. So you want to find some balance. And the next method I'm going to present is the last method we are learning. It's a very popular method that strikes a balance between accuracy and computational cost. So this is the Runge-Kutta method. Fourth order Runge-Kutta method. And I'm just going to give the definition here. So here, xn plus 1 equals x of n plus 1/6 of k1 plus 2 times k2 plus 2 times k3 plus k4. And I will give the definitions of these parameters. K1. So this is just the same as in the first order method. This is f of x of n plus half of k1 times delta t. K3 is f of x of n plus 1/2 of k2 times delta t. And k4 f of x of n plus k3 times delta t. So when you calculate this, you must do it sequentially. You must get k1 to calculate k2, and you must get k2 to calculate k3, and k3 to calculate k4. And then this, here you see, this is a kind of weighted average on all of them. So it'll take you more time to run this on a computer, at least 4 times. The time it will take you for a first order method, but the errors are smaller. And what you need to be careful about when you take your DT is not to take a DT that is so small that your computer starts rounding your numbers. So everything here is multiplied by dt, right? So multiplying by dt can give you very small numbers, and sometimes this requires higher precision than what you have in your variables in the program. So it starts cutting off your last digits, and you are accumulating errors just due to the limitations of the implementation in the computer. So you might see this in the next exercise, in the simulations that you run.
But when you say that D too small, what would be the measure? How will I know I'm exaggerating?
Well, I hope that in the exercise you'll get some feeling for that. Usually you won't take such a small delta t because the simulations will just take you so much time. If you're actually running a real model and you need to do many simulations, usually these delta t's that give you the round off errors are smaller than what you will choose. The important thing is to be at least one order of magnitude smaller than the smallest time constant in the system. Okay, since we have some more time, I want to start the subject of bifurcations. Where is... I'll do it here. So I told you that one-dimensional systems can produce monotonous flows with no oscillations. But there is one complication to these systems, and that is parameters that you insert into the equations. So, for example, you might get, I'll write it as x dot, you might get something like this. X dot equals x squared minus 4, or 3x squared minus 4. So these numbers can be very critical in determining the behavior of the system. And right now we'll treat not specific numbers, but parameters. So as if when you receive an equation with numbers, then they are actually parameters that were given a specific numerical value. When you deal with physical systems, then these parameters will be, for example, your sodium conductance, your calcium conductance, your time constants, a membrane time constant, number of neurons in your network, and so on. Some physical, some values of constants from the physical world. And then you want to know how your system depends on these constants from the physical world. So what I'm going to show here is that depending on these values, you might get different fixed points. As you change some parameter, you might have fixed points appearing or disappearing or changing their stability. And these qualitative changes in numbers and stabilities of fixed points are called bifurcations. And we start with the most simple bifurcation.
Can you repeat the definition?
What?
Can you repeat the definition?
Definition, bifurcation is qualitative change in dynamics in a system's dynamics as a parameter is changed. And examples: number of fixed points, stabilities of fixed points. I start with the simplest bifurcation, x equals r plus x squared, with r a real number. And we will start considering several cases that will show us that this could give rise to different qualitative behaviors. So say r is smaller than 0. I'll plot here the phase portrait. So this is r. It's smaller than 0. And in the phase portrait, I have two fixed points, one stable and one unstable. Right, this is my diagram. So x star equals plus minus square root of the absolute value of r. Now say that r equals 0. So this is just x dot equals x squared and like we saw today, this is a half-stable fixed point. X star equals 0. Now say r is larger than 0. And now I can still draw the vector field, but there are no fixed points. So we can imagine that if R were changed continuously from negative to positive, then we would have two fixed points coming closer and closer until they converge into one fixed point and vanish. They kind of annihilate each other, like an electron and a positron. And even if we don't consider a continuous change in R, we can consider different systems that have different R's, and although their dynamics is defined in a similar way, they would be very different systems. So we say that our bifurcation occurred at R equals 0. This was the critical point where the fixed points met and vanished. And we represent bifurcations on the following diagram. We treat the bifurcation parameter R as an independent variable, and we plot the values of the fixed points. So for a positive R, we had no fixed points, but there is nothing to plot. But for a negative R, we had, remember, this definition of the fixed points. So we had two fixed points existing for any negative value of R, and this is the plot of x equals square root of R, and this is x equals minus square root of R. And the convention is to use a dashed line for an unstable fixed point and a solid line for a stable fixed point. So this type of diagram is called the bifurcation diagram. And we can see in it that the bifurcation occurs at R equals 0, and I usually mark this with RC. The critical R was 0. Critical.
This is for this function or generally?
Excuse me?
This is x versus r for this
For
function?
this function. For any bifurcation of the